Graph neural networks, GNNs, have emerged as a powerful tool for analyzing and modeling complex relational data, with applications in various domains such as social networks, biological networks, and recommendation systems. Despite their capabilities, GNNs face challenges like oversquashing, underreaching, and oversmoothing, which limit their ability to effectively capture and propagate information across dependencies. To address these limitations, this paper proposes a novel approach that applies renormalization group (RG) theory to devise a new graph rewiring method. The renormalization group theory is a powerful language for studying complex systems, providing a framework to systematically study the behavior of complex systems across multiple scales. By employing RG techniques, researchers can gain a deeper understanding of collective behavior and tackle arduous problems like critical phenomena. However, to date, there are no methods that employ renormalization group theory for graph neural networks. This paper aims to fill this gap by developing a method that represents the input graph at different granularities. Instead of considering only the smallest granularity, where each node and edge in the graph is visible, the proposed method allows the GNN to also look at larger granularities, where nodes are grouped into clusters, and it's possible to study the relations between these clusters. This approach enables the analysis of the large-scale behavior of complex networks, such as the internet, social networks, or biological networks. The contributions of this work include introducing the concept of applying renormalization group theory to graph neural networks, an extensive experimental section to back up the claims, and laying out the foundation for a new research agenda that aims to borrow theoretical properties from the renormalization group to enhance current GNNs architectures. In the realm of graph neural networks, GNNs, a pivotal challenge lies in the development of a comprehensive theory that can effectively handle complex graph structures. This paper introduces an innovative approach to address this issue by leveraging the concept of renormalization group, a technique commonly used in statistical physics. The proposed method, dubbed Laplacian renormalization group, LRG, operates on the principle of identifying clusters within a graph and then reorganizing them into supernodes, thereby simplifying the graph structure. The paper commences with a brief introduction to the fundamentals of graph theory, including the definition of a graph as a pair, V, E, where V represents the set of nodes and E denotes the set of edges. It also elucidates the concept of the Laplacian matrix, which plays a crucial role in the computation of information diffusion trajectories. These trajectories are utilized to identify clusters of nodes that reciprocally process the same information, leading to the formation of a metagraph. The authors then proceed to elucidate the process of real space decimation, which entails substituting each cluster with a single supernode, thus resulting in a decimated graph. However, this approach has its limitations, particularly concerning the handling of node features. To overcome these challenges, the authors propose a novel perspective on LRG, viewing the decimation procedure as a rewiring process instead of a node reduction process. This alternative viewpoint involves increasing the number of edges in the graph rather than reducing the number of nodes. Specifically, all nodes belonging to the same cluster are required to share the same incoming and outgoing edges, as depicted in Figure 1. This is achieved by computing a new adjacency matrix ** operator, whose elements are determined by the product of the original adjacency matrix A and the metagraph matrix zeta. Consequently, the neighborhood of a node U in the rewired graph is redefined as in U equals ZW, U, union, V element of MWZ versus, where ZW represents the set of nodes that compose the supernode W. The authors emphasize that the proposed approach can be applied to various GNN architectures, including those that employ message passing, attentional, and convolutional paradigms. They also underscore the significance of the learnability of the renormalization of the features of each original node into the features of the supernodes, as well as the need to prevent oversquashing. The paper concludes by highlighting the potential of the proposed method to enhance the understanding and efficacy of GNNs, particularly in scenarios where the graph structure is complex and dynamic. This research paper presents a novel approach to improve the performance of graph neural networks, GNNs, on large-scale graphs. The proposed method, referred to as Laplacian renormalization graph, LRG, operates by rewiring the original graph into a smaller version, known as the decimated graph, while preserving the original graph's spectral properties. This process is visualized in Figure 1, where nodes are clustered into supernodes, and the graph is rewired so that nodes within the same supernode share the same incoming and outgoing edges. The authors also introduce a dual setting for their model, where two graphs are fed into the network, one that has been renormalized and another that remains unchanged. This dual configuration allows the network to encode graphs at two different scales, providing more comprehensive information for prediction tasks. The experimental setup includes 4 popular benchmarks: Quora, PubMed, CiteSeer, and Amazon Photo datasets. The authors compare their method with other state-of-the-art methodologies, such as HEAT and PPR, as well as a vanilla baseline. The results demonstrate the superior performance of the LRG method across all datasets, with the Quora dataset showing the largest nominal markup. Interestingly, the optimal scale, tau, varies across different datasets, aligning with the LRG theory that different networks have different characteristic scales. The proposed methodology integrates the renormalization group, RG, with current graph neural network, GNN, practices, enhancing the performance of GNNs in various benchmarks. By applying a rewiring procedure, the GNN can view the input graph at different granularities, providing insights into its overall structure and behavior. This approach has been experimentally verified on different benchmarks and baselines, showcasing its potential to understand how the properties of these networks change as we zoom in or out, helping identify universal behaviors. Our method addresses some of the most significant limitations of GNNs, such as underreaching and oversquashing, which are related to propagating information between distant nodes. By varying the distance through the parameter tau, our approach can alleviate these issues. Additionally, it could be seen as a filter on the graph Laplacian higher frequencies, significantly reducing the noise problem that naturally emerges in GNNs. The experimental results indicate that our rewiring procedure is highly effective in terms of performance, reaching up to a 12.1% improvement. This enhancement underscores the value of our approach and its potential impact on the broader research community and related applications. However, some limitations exist, including the requirement for undirected graphs with a single connected component and the need to reduce the dimensionality of node features in certain situations due to increased edge density. Future work will focus on limiting the increase in edge density to make the procedure more practical. Furthermore, the proposed method has the potential to solve some of the GNN's most severe limitations and could be used in many other problems of both geometric deep learning and general deep learning. This study aims to lay out the foundation for a new research agenda that aims to borrow theoretical properties from the renormalization group to enhance current GNN's architecture. The paper presents a comprehensive overview of the current state of graph neural networks, GNNs, focusing on their limitations and potential improvements. It begins by discussing the concept of oversquashing, which refers to the phenomenon where GNNs fail to differentiate between nodes in a graph as the number of layers increases. This issue is attributed to the bottleneck in the GNN architecture, where the network's ability to propagate information is limited by its depth. To address this problem, the authors propose a new perspective on GNNs through the lens of geometric deep learning. They draw parallels between GNNs and traditional deep learning models, highlighting the importance of considering both spatial and temporal aspects when modeling complex systems. The paper also emphasizes the role of curvature in understanding GNNs, suggesting that it could be a key factor in explaining oversquashing. In addition to these theoretical insights, the paper provides a thorough review of various GNN architectures and their applications. It discusses the use of GNNs in tasks such as traffic forecasting, community detection, and personalized recommendation systems. Furthermore, it highlights the importance of considering the graph structure and its properties when designing GNN models. The paper also touches upon the concept of renormalization group, a theoretical framework used in physics to study phase transitions and critical phenomena. By applying this framework to GNNs, the authors aim to develop a more nuanced understanding of how these models process information and how they can be improved. Finally, the paper concludes with a discussion on future research directions, emphasizing the need for further exploration of geometric deep learning techniques and their potential applications in different domains. It calls for a more systematic approach to understanding GNNs, one that takes into account the interplay between network architecture, data properties, and the underlying geometric structure of the graph. The research paper discusses the equivalence between computing the update function of a graph neural network, GNN, on a node of the rewired graph and computing a GNN update function on a node of the decimated graph. It begins by defining the decimated graph as composed of supernodes obtained by clustering the nodes of the original graph. The rewiring procedure is designed to create for each node in the original graph a neighborhood that includes its original neighbors and additional nodes from the supernodes. The update function of a message-passing GNN is then analyzed, showing how it can be rewritten in terms of the decimated graph. This involves defining new neural networks phi and psi, which are used to transform the original update function. The proof involves a series of algebraic manipulations, utilizing the properties of the Moore-Penrose inverse and the linearity of the rows of the matrix W1. The final result demonstrates the equivalence between the original and decimated graph update functions, highlighting the significance of this finding in the context of GNNs.